Welcome to the first lecture in this trigonometry class, and we're going to talk about angles and degrees and special triangles. And some of these topics you're going to be familiar with already, such as the Pythagorean theorem you have come across before. So what's going to happen here is in the first two sections are some topics that you're already familiar with. Here's directly from the book that we're using at the time of recording an example, and it says, well, there's a ski lift, or there are ski lifts at Tao Ski Resort, and one of them is called the Bear Paw Double, and it has a vertical rise of 120 feet, and the ski lift itself is 790 feet long. Determine the angle. That's what trigonometry is for. We're barely starting out here. We'll encounter the sine, cosine, and tangent in the third section. So what I'm going to do right now is I'm just going to use a protractor, hold it onto my screen, and determine the angle manually. And when I do that, I come up with 8 degrees. So I have 8 degrees measured. What you just saw, I continuously do that as well. Please get used to it that I copy and paste things here. That just saves me some time in trying to type as I'm typing along here. So I measured 8 degrees, and as I said, later on we'll learn how to do that with cosine, sine, and tangent. Let's look at what kind of angles we have, and again, you're probably familiar with these here. We're familiar with a right angle that is 90 degrees, that the straight angle is 180 degrees, then an acute angle is less than 90 degrees, then an obtuse angle is greater than 90 degrees, that complementary angles, alpha and beta, sorry about this strange symbol here, that these two add up to 90 degrees, while supplementary angles add up to 180 degrees. And everything that I just showed you, I'm going to go to paint. You will frequently see these paint or graphing calculator in italics, which are just a reminder for myself that I want to use a different program. So I'm going to get out of Word and go to Paint, where I have already opened some graph paper. And so I'm going to draw them here, for example, a right angle. So there and there makes it relatively easy to make a horizontal and a vertical. I know I have a right angle, and then of course this here would be a 90-degree angle. The straight angle would be this one here. So I'll make one here, make maybe a point there, and make one here. And now I'm going to draw on the angle, and this one here is 180 degrees. An acute angle, well, as we said, as long as it's less than 90 degrees, and I think we can definitely see that this one is less than 90 degrees. An obtuse angle, here I don't have to be too careful in order to make a horizontal line, because we're just using some random examples. So there we go. A complementary angle, here I am careful about making a horizontal line first and then a vertical line, because complementary angles add up to 90 degrees. And now I'm going to make some kind of random angle in here, and then the angle alpha that I might have here, plus the angle beta that I have here. These two add up to 90 degrees. I could measure here, so alpha is roughly on my screen 24 degrees. That means beta comes out to 66 degrees. By the way, if this is a little bit off your screen, all you have to do is push the what was it called, the column at the bottom, or the row at the bottom, where you push a little bit over, in order to get it on the screen. On everything that I see, you see as well, or you should be able to see. Okay, I think it's called a scroll bar. There we go, the scroll bar. Sorry about that. So let's say we have the supplementary angles. So here I have this one here, and now again we're going to make some kind of angle in here. Example, this one, and then again we have here an angle alpha and here an angle beta. And again, I can measure here manually, and I come up with that I have approximately 68 degrees for alpha, and that means that beta needs to be 112 degrees. So what I just explain in Word here you see as a drawing. Before I forget, I might as well save this one here. You might just see a gray box, but as I said, I don't want to forget about it. Okay, go back to Word. Of course, the advantage of recording my sessions is that you can go back at any time, that you can stop, that you can take a pause. And that's a little bit of an advantage over a normal lecture where you just have to pay attention all the time here. But here in this record session, you can go back at any time. Right triangle. You're familiar with those, I'm sure, that in a right triangle, Pythagorean theorem applies a squared plus b squared equals c squared, and I'll show that in just a moment, again, using paint. And soon we'll see that cosine and sine are actually related by the Pythagorean theorem, and that'll be in a few sections down the line. Let's see. Let's go over to paint, and we'll get a Pythagorean triangle. Open a new one here. If you see a gray box, then that's simply there's some pop-up boxes here. They might only up as gray. So let's do a right triangle here. Again, that works best if I use a horizontal and a vertical. There we go. We have a right triangle with A, B, and C. So you can write A equals, and I'm going to measure this here manually in inches, and I come up with pretty much 2.75 inches. And then I have B equals also 1.75 inches. Just so happened. Might be a different scale on your computer screen, so whatever I measure might not be exactly the same that you measure. And then C, which I may measure at, this would be the hypotenuse, as pretty much 3.25. Seems like I got quarters and 3/4 of inch. 3.25 inches. So if I keep these three numbers in mind and go to the graphing calculator, which I just have lying here on the side. So I'm going to type in 2.75 squared plus 1.75 squared, and that should equal c squared. Respectively, I come up with 10.625, and I take the square root of 10.625. I come up with 3.26, which is pretty much what I measured here, or pretty close. I mean, they're really close. Obviously, I cannot measure as good, but pretty much. Okay. Let's go back to Word again. I don't want to, before I do that, I don't want to lose this drawing here. I'm going to paste it in later on. So let's go back to Word. My graphing calculator, by the way, is lying on my desk here. in later chapters we will do. We will actually look at a graphing calculator on screen. But for now, it's fine that I just have it lying on the side here. Okay, here's some examples, and for the Pythagorean, so that, for example, three squared plus 4 squared equals 5 squared, and you can easily check that out. Or that, for example, 12 squared plus 5 squared equals 13 squared. So you would have a triangle with 12 inches long, 5 inches high, and then the hypotenuse comes out to 13 inches. And I can also show that in Paint. Let's see. Oh, there it is. So if I take one here that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 boxes long, and then 5 boxes high, then this here should be 13 boxes long, but of course it's hard to see here. But that's the one we just looked at. And again, I can write on here that this one is 12, this one is 5, and this one is 13. Back to Word. Or, for example, 15 squared plus 8 squared equals 17 squared, and you can easily check all of these. These here, as you can see, there are lots and lots of integers you can choose. There's a certain method to the way you can do that, so I did that ahead of time. You just have to see that as you take a couple of squares, like 17 squared, 15 squared, that the difference between the two is also a square. There are many more examples. 6 squared plus 8 squared equals 10 squared. Or it doesn't have to be integers, so 6 squared plus 11 squared comes out to, that would be 36 plus 121, which is 157. Take the square root of that out of that, and you come up with 13.6. Oh, rounded. The proof of the Pythagorean theorem, there is one supplied in, or a couple supplied in the book. One of them is by President James Garfield from 1880, who did that proof when he was a representative. And I'll do that in an additional live session. Let's look at some special triangles, such as the 30, 60, 90 degree triangle, and already got it from Paint here, pasted in here. And the proof is in the textbook. And when you have side t equals 3, then the other side here comes out to t equals 3. Then the other side, t times the square root of 3, and I have to borrow a square root from somewhere. See if I find one. So t times the square root of 3, and I do that on the side. So 3 times the square root of 3 comes out to 5.2. And then 2t, of course, would be 6. And then again, when you try that, let's see, I'm going to borrow that. This one here. You come up with 3 squared plus 5.2 squared is the same as 6 squared. So that's a 30, 60, 90 triangle, a 45, 45, 90 triangle, where we have t equals 3 on one side. Of course, it has to be t equals 3 on the other side. And then the proof here, actually, we can do sleight of hand. where we say, okay, t squared plus t squared equals, well, 2t squared. Take the square root out of that, which is the hypotenuse. We come up with t times the square root of 2, respectively. 2 times, I'm sorry, t times the square root of 2 is going to be 5.2 rounded. I'm just going to do it on the side here. Square root of 2. Oops, 5.2. 4.2 rounded. And again, the Pythagorean would look like this. 3 squared plus 3 squared equals 4.2 squared. And with that, we're concluding the lecture on this first section.